Hi, welcome along. What I believe to be our last video on quantum phenomena, photoelectric effect. Realise quite importantly, there's a bit of terminology that I've missed out. So what I'm going to do is just set this to red light, and then we're going to turn up the intensity. The light that's being generated here is monochromatic. So mono means one, chromatic means color, one color. But we would say that as one wavelength. If you're after in the exam, you say all the light is a single wavelength. So we've got a monochromatic light source. We can vary the wavelength of that light source. We can vary the material that it's shining on. That's over here. And then you can see we've got a circuit, and we'll look at the circuit later, but we'll just keep it simple at the moment. So let's stick the intensity up high. Looking at sodium metal, so we don't anticipate we'd need particularly energetic photons to remove electrons because sodium's a fairly reactive metal, so it should be fairly easy to remove electrons. So we're just going to go down to the other end of the visible part of the spectrum, and then suddenly you can see there are electrons being produced. So let's do a kind of bit of basic noticing. Are all the electrons produced traveling at the same speed? No, clearly they're not. Some are definitely going faster than others. So why are some electrons going faster than others? Well, we talked about this before. Um, the energies of the photons are all the same, but some electrons are easier to remove than others. So some electrons take more energy to remove them from the metal surface. They'll be moving slower. The fastest electrons are the ones that the maths is interested in because they took the minimum energy to be removed. So they only required the work function's worth of energy. Quite a common basic language mistake that students make is that they think that it is always the work function, the amount of energy required to remove an electron from the metal surface. It always means the minimum amount of energy to remove an electron from the metal surface. What happens if we halve the intensity? Okay, so we've now got half the photons per second. So I'm hoping, it's not particularly convincing, that we've got half the electrons being produced per second. A check on that would be looking at the current. That's a measure of the number of electrons per second. We've got 0.064. So let's just double that up. Yeah, and you can see that roughly that's doubled the current. So twice as many photons per second is liberating twice as many electrons. We can try and get a feel for the threshold frequency, or which wavelength will just remove electrons from the metal surface. So you can see as we come down into the greens, the currents come down. Okay, so we've now just those photons just about have enough energy, but we've got a lot less electrons because they've got so much less energy. Go a bit further. Right, we've now clearly crossed over and we spent long enough on it, we could work out exactly what was the longest wavelength capable of removing an electron. So let's go back to where we are removing an electron. We will have a look at the battery in a moment. So let's just swap the metals now. So let's swap from sodium to zinc like we saw in the initial demonstration. And just like the initial demonstration, visible light, 130 nanometers is visible light, is not capable of, the photons have insufficient energy to remove an electron from the metal surface. We have to go out into the ultraviolet to start removing electrons from the metal surface. There you go. If we go to copper, which is even less reactive, even harder to remove electrons, we stop the process again. We'd have to go even further into the ultraviolet to get any electrons out. It's easiest for this next bit to go back to sodium. And we're going to have a look at this battery arrangement here. So at the moment, the electrons are being emitted here. They're being picked up by this piece of metal and they're flowing back around the circuit. And we're imagining there is no battery, but we still get a current because those electrons want to go back to where they were. If we turn the battery around this way, what I've done is I've made this plate very negative and the electrons come out and they haven't got sufficient energy to cross the gap. So our current falls to zero. If I turn the battery round, That encourages the electrons to come across, although of course doesn't make any more electrons, they're just going a bit faster. So let's look at it the other way around, and then, so 1 volt is sufficient at that energy. So let's just give the electrons a bit more energy. So the more energy we give the electrons by giving the photons more energy, the further across the gap they're able to move. So we would be able to, if we just keep, right, so we've now got a current reading. So that just shows us we've now, the emitted electrons have got an energy of more than 1 electron volt. So by playing around, either changing the voltage or the wavelength, we can find the get a measure of the kinetic energy, and then we could generate some data, and we could create a graph like you saw in the previous video, and that would enable us to work out the threshold frequency and the work function for this metal. I think that all you need to know for the moment is that the reading, the voltage of the battery when the current is just fallen to 0 is a measure of the maximum kinetic energy of the electrons in electron volts. And I just thought it was a good idea for you to see something visual, just so you can get a better feel for what's happening in the photoelectric effect. Thank you.